Hey guys, this is part 2 of our conversation about what is an explanation with our guest neuroscientist philosopher David Barrick. For this conversation, we read David Kaplan's paper, Explanation and Description in Computational Neuroscience. And just to refresh your memory, in part 1, David gave us a little bit of the history of the concept of explanation in philosophy. And we also talked about computational chauvinism, which is the idea that the mind can essentially be explained independently of the brain, and that higher levels of explanation can be autonomous with respect to lower ones. We also ended by defining the 3M model, which is the major contribution of this paper. And I gave an objection that I had to that model, and we're going to pick up part 2 with David giving his objections to it. So I just want to read again the definition of the 3M model so that that's in your mind as we go into part 2. So the 3M model says that a model of a target phenomenon explains that phenomenon to the extent that A, the variables in the model correspond to identifiable components, activities, and organizational features of the target mechanism that produces, maintains, or underlies the phenomenon, and B, the perhaps mathematical dependencies posited among these perhaps mathematical variables in the model correspond to causal relations among the components of the target mechanism. So my issue with this that I said at the end of part 1 is just that it seems perhaps a little circular, or that you need to know the right answer to know if your model is mechanistic, because it needs to correspond to the true parts in the real world. And so now we're going to hear David's objections. And just to warn you, there's a little bit of audio issues in this second half, so if you hear something weird, it's us and not you. Enjoy.
Okay, so what are yours?
So I have a couple. So first, as a philosopher, when I'm wearing my philosopher hat and I look at a constraint like this, I try and understand the logic underlying the constraint. And it says a model of a target phenomenon explains that phenomenon to the extent that, and then he lists the two conditions. And I think to myself, now what is that? What is the logic here? A model of a target phenomenon explains that phenomenon to the extent that such and so. And one way to understand this is as a conditional. It's to say, if a model M of target phenomenon phi has this property of being explanatory or something like that of a particular phenomenon, then the variables in the models, et cetera, et cetera. And so one way to understand this claim is as a conditional. The underlying logic of the claim is a conditional. And then I think to myself, all right, well, what makes a conditional wrong? When is it true and when is it false? And conditionals are a little weird in logic, and there's different ways to understand conditionals.
But for the non-logic grounded people, conditionals are just if-then statements, basically.
If-then statements, that's right. But one thing I might say is, well, are there models of target phenomenons that we take intuitively to be explanatory, or that scientists take to be explanatory as revealed by their practice, that don't have these conditions? And that's one way for a conditional to be wrong, is if you satisfy the first part, the if part, but you violate the then part. In other words, if you satisfy what's known as the antecedent, but you don't satisfy what's known as the consequent. And so I think about this, and I'm saying, well, are there models of target phenomena that explain those phenomena, but that don't have these two mapping properties, these two correspondence claims? And I think there are.
Well, so I want to throw in just before you get to it. I mean, this does. There's a whole other discussion going on in the paper where he talks about sort of phenomenological models versus explanatory models, and we almost have to get at this to get to the point that I feel like you're inching at. Which is, right, like, if you just were to describe something that goes on, not explain, but there's basically a distinction between explain and describe. Like if you can predict what's going to happen, or like forecast or predict, or like even in sort of contemporary prediction where you see some things and then kind of know what other things are going to be, that's different than explain it. You might be able to do prediction without explanation. So, sorry, I just wanted to interject that before you continue.
Yeah, no, it's an incredibly important point, and I was getting there. So, but that's exactly right. So, in the philosophy of science, I mean, this is a major tenet, is this idea that there's what are known as merely descriptive models. So, to be clear, an explanation is a type of description. Philosophers think of descriptions as just sets of sentences, and they have content, they have a subject matter, they're about something. Typically, they're about the same thing if you're describing one thing. And there's some descriptions that explain and some that don't. And in the philosophy of science, there's this distinction. That distinction, is called like a explanatory model versus a phenomenological model. And the idea, as you just mentioned, a phenomenological model is it's just a description. You're just kind of saying what you saw. It's like a succinct way of saying what you saw. As Kaplan himself puts in the paper, it's a mere curve fitting exercise. You just sort of slapping together a model that can capture the observations. Whereas something that can explain, it has all these additional features, some of which Kaplan talks about.
So, a question I have, so just to sort of ground this a bit, because we're talking about computational science, we're talking about things that pertain to sort of the kinds of equations you might see in physics. A phenomenological model, and he brings up some that are explicitly equations. When you say a phenomenological model is a set of sentences, if we generalize that, it's like a set of statements, where a math equation is a statement. So if you say force equals mass times acceleration, so a basic kind of Newtonian mechanics kind of principle, you're making that's a sentence, it's a statement that says force equals mass times acceleration, and that means something formally, mathematically, whatever. But it's basically just a statement about the relationship between things that you observe in the world. So it's descriptive, it's observational.
That's right.
It's not an explanation.
And just observational, right? And he wants to make the claim, and I think it's a good claim, but I think it's hard to cash out, that those merely observational statements, they don't explain. Yeah. You need something more. Yeah. You need some added sauce.
So, but I in a deep way, I haven't yet reconciled if I know what that means. I feel like most statements made in science are descriptive. Like most formal statements.
Yeah. So that's something that I was one of my objections. But going back to 3M, just to connect this back to 3M, he wants to say that these merely descriptive statements don't explain because they don't satisfy this 3M condition. So 3M is meant to be a necessary constraint. It's in order for something to be an explanation, it has to satisfy 3M. Now, my first objection was that, I think there are things that explain that don't satisfy 3M. I want to turn that around now and point out that I think there are things that do satisfy 3M that aren't explanations. And it's not so obvious to me that even the examples that he gives of what we are calling descriptive or phenomenological models, just these mere statements, don't satisfy 3M. So he talks about the Balmer equation, and the Balmer equation is this sort of classic example of a mere curve fitting exercise. He talks about the Nernst equation. So I think let's focus on the Nernst equation because that's actually in neuroscience. And the Nernst equation is just a statement about resting potential. It's voltage, resting voltage when it's... So
as grounding, neurons have a membrane. They're a cell that has a membrane, and the cell has a resting, kind of like a battery. It has a voltage potential across the membrane. So and this is due largely to there being different levels of ions on the inside and the outside of the membrane.
So the Nernst equation just tells you, based on ion concentrations, what you should expect the resting potential to be.
Right. If you measure the voltage, what would it be? And I actually thought this was a confusing example of a phenomenological model.
I'm actually convinced it's not a phenomenological model. So to be clear,
I am as well.
Yeah. Okay. So he
wait. I'm gonna guess that it's for different reasons.
So the author
might be, but
so the author posits that the Nernst equation, which describes the relationship for largely between the voltage across the membrane and the concentration of ions inside and outside of the membrane. So those are these are bulk statistical variables. It's what's the concentration of potassium inside versus outside the cell, and what's the voltage of the membrane. And these are all sort of bulk statistical phenomena. And
so let's really talk about this with an eye towards this 3M constraint, right? So I think that the Nernst equation satisfies 3M. Now, you might not agree with that.
Well. So let's be clear. The author thinks that the Nernst equation, or asserts the Nernst equation, is phenomenological, and there's this whole complexity, right? So there's more nuanced layer to this. part of the definition of there's multiple definitions of phenomenological. A definition of phenomenological that I found when browsing the internet before starting this conversation was basically like, if you can derive the law from fundamental first principles, then it doesn't really remain phenomenological. So there's a statement like, this is clearly a description of the relationship between variables that are sort of like bulk like variables like concentration and voltage. And it just is a description of the relationship between those variables. So in that sense, you'd say, oh, it's phenomenological. But you actually can derive this from like more like low-level fundamental laws, right? You can use statistical mechanics basically to derive the Nernst equation.
Right.
And that's not something that's acknowledged in this paper.
That's not acknowledged in this paper. So like you can use like, sort of the Boltzmann equation and that kind of standard like thermodynamic statistical mechanics kind of approach to go from more fundamental laws of physics to this equation, and you can just outright derive it, and they do that in statistical mechanics classes.
Great. So I think that's a good point. I think there's a whole host of issues about actually trying to get a very firm handle on the difference between a phenomenological model and a descriptive one. Actually, I'm not certain there is really any difference.
Oh yeah, I thought that those words were interchangeable, descriptive and phenomenological. Is that not?
Sorry. A phenomenological model and an explanatory model. Okay. I apologize. Descriptive model. Yeah. They are. The reason I am not sure there's really a deep distinction between merely descriptive and explanatory models is very much for reasons I mentioned earlier about how what's autonomous and what's not autonomous kind of can depend on what level you're at. I kind of think the same thing a little bit about this descriptive versus non-descriptive point. I think that, at one level of description, your model might be explanatory because you're talking about smaller stuff down below, so to speak, at the lower level. Engaging for a second in the myth that there are these well-ordered levels anyways. But if you go down to that lower level, that very same model now it's merely phenomenological. It doesn't explain anymore because now you're sort of hanging out amongst those low-level things, and now you're just describing their behaviors. You haven't really given the kind of meaty, substantive background or foundation for the claims that something like the distinction is meant to latch onto. I also think, though, that if you compare the Nernst equation to some of to the content of the 3M constraint, I think it might satisfy the 3M constraint. Because it says, recall that the 3M constraint says that the model of the phenomenon has variables in the model, has variables in it that correspond to things in the world, like, I don't know, say ion concentrations, for example.
Sure.
That's a thing in the world. Or an electrical charge. That's another thing in the world. And then, so there seem to be aspects of the Nernst equation that satisfy the first constraint, the first condition in the 3M constraint. And then the second condition is this one about these mathematical dependencies that hold amongst the model variables should correspond to causal relations. That one is a little trickier, but there's no question that there are mathematical operations present in the Nernst equation, such as taking the natural logarithm and division and things like that. And it turns out, and this is what connects to what you were saying, Josh, it turns out that there's good reasons for these relations that come from the first principles.
Yeah, so this is related to the idea that, okay, so... Yeah,
that's right.
So, but just to be clear, because this I think makes it actually more confusing, physicists, as far as I understand, refer to phenomenological models in physics in a way that's different than the way philosophers do. So I believe like the laws that are derived in statistical mechanics are often referred to as phenomenological models in physics.
Oh, interesting.
In that sense, like the Nernst equation is probably, like physicists or whatever would probably refer to it as a phenomenological model, and I believe that has to do with a couple of things. And so this gets into something that is discussed in this paper and is interesting, and I know Grace was curious about this too, which is like if the model was first discovered, not from first principles, but like if you were just a dude in a lab and you played around with the chemistry and the concentrations, and you had electrodes in your water and you observed a voltage, right? Then you would have been just coming up with the phenomenological like description, right? You wouldn't have known why it was the way it was. You would have just said like, oh, I added more potassium to this side of this artificially separated system, and my electrodes tell me that there's now some voltage. And that kind of setting is like, that is experimentation. That is like the way you did it is observational, and you're merely describing in mathematical statements the relationship between variables that you empirically observed with no knowledge of the first principles. And like a lot of, like historically, many physics laws, many chemistry laws, right? Like relationships between pressure and temperature of gases or things like this have been figured out sort of empirically that way. And so you might view them as phenomenological. And then you might subsequently, like later, figure out a derivation that explains why those laws are the way they are. So that's one point. But then there's a second point as well, which is in addition to like there being this sort of two-step process where you first experiment and then subsequently prove it, it might also be the case that the quantities involved are inherently statistical quantities, right? So when you're talking about concentration and voltage, there's a sense in which those are like real things in the world, but there's a sense in which those are sort of like, we know them to be sort of bulk properties of things. This is, I think, inherently philosophical, but the question of like, what is the concentration of something? Well, if we believe it to be like something related to how much of some kind of particle is dissolved in some kind of, solution, then to even talk about quantities that are these sort of statistical descriptions, you might just throw up your hands and say, this isn't a lowest level kind of mechanistic thing. This is a phenomenological model because I can only use sort of very coarse measurements to even describe this. And so I think there's a sense in which like all of the principles that are sort of like you would derive from statistical mechanics like this, you might think of as inherently phenomenological because there are underlying mechanisms. There are forces between the particles at the low level, but like at the high level, you're observing these relationships between these variables, and you might be able to derive, like in probability, like as statistical descriptions, why those macro variables relate to those micro variables. But you can't help but call those sort of macro variables phenomenological in the sense that they're sort of statistical descriptions of the state rather than the state itself.
I don't know if I'm convinced by the second point, that because it's a statistical mapping from some lower level to a higher one, that it has to be called phenomenological. I mean, I can see how it's like somehow different than a non-statistical mapping, but I think you can still call that mechanistic in some way. If you know how to do that mapping, you can say that this is a mechanistic.
So I don't know. I think this is something that at least feels one could consistently press on this point, right? Like I'm not sure exactly how I feel, but it does seem like if the phenomena that you observe is a statistical property of things you know to be lower level stuff, then like you might just say that isn't mechanistic. What's mechanistic is at the lower level, and I can explain that. So this maybe gets at the distinction between explanation and descriptive. Like I think some of these things that which you can derive from low level things are explanations, right? Like you can explain the Nernst equation is explanatory in the way that David was talking about, but maybe it is still a phenomenological model. So it's an explanatory phenomenological model.
Because that wasn't an option.
Yeah, right. That wasn't one of the categories that was put forth in this. But
well, I mean, that's basically the point I was trying to make earlier. That I'm not even sure there is a strong distinction between the phenomenological models and the
there are definitely other models, and so this comes up in neuroscience as well. Like, let's say you just do linear regression and predict a neuron's activity from an input image or something like that.
Yeah.
So especially if you're thinking about a neuron that's like deep in the brain, like through many layers of visual processing, it's very far removed from the input image, but you can still try to say what its activity will be based on the input image.
So there's this deep in the brain neuron, and you're gonna like look at what stimulus impinges upon the retina, and you're gonna try to predict the neural activity, but you're gonna only use linear regression to do this, right? If you do that, you're doing something that is producing a descriptive relationship of the input to output. I think you could call that a phenomenological model. You could call it a descriptive model. It's certainly not a causal model in a deep sense. It's like very weakly statistically causal in the sense that like the input produced the output in a way that was like vaguely sensible. You might have like a time lag in your regression so that like what happened on the retina, like, 30 milliseconds earlier.
I mean, these are the questions.
Yeah,
these are really important questions. I was going to say, what happens if we do a little bit of a GLM here and we move to like a log linear link function with Poisson distributed noise? So in other words, if we do a type of linear regression.
Yeah, so like a version
that
of
builds
linear
in
regression.
more knowledge, even though it still feels descriptive, it also isn't, because the choice of the function, just for the listeners, like we're modeling these neurons' activity as a function of the input. And Josh was saying, well, what if it's a linear function? And what I'm saying is, well, what if it's like a fancy linear function? Is it still merely descriptive then? Because the choice of the way that I'm transforming that linear
includes
operation,
domain knowledge or whatever.
Yeah, and I think
it builds in theory and background knowledge and things like that.
we can take that even farther and say, well, what if it's some kind of nonlinear regression that effectively involves pulling out the features in the image that really are what make the neuron fire in some way? Like, then we have like a deep neural network, which people do use, or at least I think of as mechanistic models of the visual system. So it is a continuum of some sort that you can just... That's why when I asked earlier about functional analysis, this idea of whether the levels of the function should map to levels of the physical stuff, it just seems to me that if you've done a good job of capturing the thing you're trying to explain, the parts of the model are going to relate to something. Like, you can't do a good job of predicting without it being related to what's really happening.
Totally. And this comes up most obviously for me with regard to the Hodgkin-Huxley model, because he wants to say of the Hodgkin-Huxley model, which is a model that of the membrane potential.
So this is like the Nernst equation on steroids, basically. It's like
that's right.
It's if you have an axon, if you have a membrane that is transmitting the signal from one neuron to another, this explains the sort of dynamics of the voltage over time and space. So it's a sort of more like a partial differential equation. So it says like, how does the voltage of the membrane change as a function of time, and how does it propagate through space as you transmit a signal from one cell to another? That's right,
and it's a famously successful case of, I would contend, explanation in the neurosciences. And what Hodgkin-Huxley did, they had very, very good data. They had a very nice experimental preparation on the squid giant axon, which is different from a giant squid axon, I'll have everyone know.
Yeah.
And because their data were so clean, they actually came up with their equation, as they say in the original papers. It was a curve fitting exercise. And if I remember correctly, might be apocryphal, but I think they actually had time on the one university computer to do this, but it was like broken or down for the day for whatever reason. So they did it by hand, I think.
I've heard that too.
I've heard they did it by like a hand calculator, like some sort of crank machine or something. I don't know.
Yeah, they used something like that.
Yeah,
and they got this equation, and it turns out that their coefficients, the rate coefficients in the equation, actually do capture the aspects of the ion channels that permit the membrane current to flow along the surface of a neuron.
Yeah, so like
now,
I think
of the axon.
To be just like very explicit about it, basically they were trying to figure out how they could describe how the voltage changes over time during an action potential, like when the neuron is actually firing. And the curve fitting aspect of this. And they wanted the shape
in particular.
Yeah.
That's right.
And the curve fitting just means that they trial and error different equations kind of and see what works, and then they ended up with something that has parameters and terms in it that we now know relate to physical elements of the neuron.
Precisely relate. So they have this one rate coefficient for the potassium conductance, which has these, it's a term n to the fourth, and they interpreted that n as the probability that something would be activated. They thought of it as particles, and it turns out it has to do with elements of the ion channels. Now, it's so interesting, this case, because there's this saying as a scientist that good data will speak for itself. And this is kind of a case of that, where even though it was merely a curve fitting exercise, even by their own admission, it was such good data, such clean data, that their curve fitting exercise still picked out what we now know to be actual mechanistic elements, even though at the time no one really had a very good idea of what's leading to the influx and efflux of ions across the cell membrane. Secondly, on Kaplan's recounting of this episode in Neuroscience, he says something like, well, it's not explanatory, it's just a predictive model. They even say it's just a curve fitting issue. But once we discovered that there really are four proteins.
Yeah, it's like 4 subunits to the ion channel.
4 subunits in the ion channel that maps on to the n to the 4th term for the potassium conductance of the model. Then he says, but then it's explanatory. And that just struck me, I don't know how that struck you guys, but that struck me as a little strange.
Well, so as I'm trying, I feel like this is consistent with maybe the way that historically physicists use the term phenomenological to the extent that they do, right? Like in the statistical mechanics sense, right? Like it's like if you first did the experiments where you like recorded the relationship between, I don't know, temperature and pressure of gases, and then later realized that you could derive that from first principles, which you can, and people figured out. I mean, and like that did happen later, right? So people first figured out the relationship between temperature and pressure of gases, and then subsequently were able to derive it. There's a sense in which that, we can decide what we want to call that, but there is a sense in which, like, originally it didn't have explanatory power, maybe. It was just a description. And later it is the relationship between the original, like, statement and the derivation somehow that, like, give it its explanatory power. Like, it's if you have both parts, It now has explanatory power. No? You still don't buy this?
I'm bothered by that because I think it still binarizes this. It's not like it became explanatory when you had the evidence, and it doesn't. It doesn't help in the sense that it doesn't. A similar complaint is it doesn't capture the continuum. The fact that a model that is more coarse-grained and doesn't map cleanly to things can still be on this continuum and needs to be refined. Like we were saying with the using linear regression to predict a visual neuron versus using a big nonlinear model. I still feel like that's a continuum, and I don't see how this framework of when you discover the such and such helps you with that continuum. There's no way to break it up cleanly.
Yeah, I think it has some explanatory power. Maybe it has more later.
Okay.
Once you can provide the mechanistic underpinnings. I'm willing to accept that it should
be a continuum.
Well, this relates to another concept he brought up for explanatory mechanisms, which is this like idea of they give you knobs to turn. Like you could know, like if I change this thing about the system, this will be what happens in return. And you can argue that you don't get that benefit until you know how it maps on to the subcompartments of the ion channels or something. The actual practical ability to manipulate based on your mechanistic understanding doesn't come until you know how everything maps to everything else. So maybe that's a way where it doesn't become a true explanation until you know all the mappings.
So I don't believe that though, right? So like if you want to make a hot air balloon work, if you know the relationships between gases and temperature and pressure of the gas, then you don't necessarily need to be able to explain why those relationships hold to be able to control the system.
No, I totally agree, and I thought that when I was reading this description that he was giving, that this kind of the ability to turn knobs is related to being a mechanistic explanation, because, and he acknowledges this as well, because obviously like in the Nernst equation, which he's saying is not a mechanistic explanation, if you change the concentration of ions, you change the voltage. And like that's clear. That's a knob you can turn. But he kind of makes this distinction between like the inputs to the model not counting as knobs that you turn because that's what you're trying to explain from the start. And I think the idea was that like if there are variables in the model that don't map cleanly to things in the world, then it's not a mechanistic explanation because those aren't knobs that you can turn. Like if there's some term in a model that's like some complicated jumble of something and it's only there to make the curve fit better, then it's not explanatory. Okay. Because obviously, like even in the linear regression predicting a neuron's activity in response to images, you change the image and it tells you how the neuron's response will change.
So you can make predictions and you could hypothetically control the system using your predictive model.
Yeah, but he's trying to make a distinction between controlling it via the inputs that you were already trying to fit to the output versus controlling it with other terms in your mapping.
Okay, so fine. So like, the parameters of the model, kind of.
Yeah.
Yeah, to me, like I feel like for mechanism, you want to make claims about causality, but this distinction doesn't really feel causal, actually.
Which distinction doesn't
Well,
feel
so
causal?
like if the input variable that you have a descriptive model of might be one of the causal variables, like whether this is explanatory or descriptive, according to whatever kind of continuum we are, provisionally going to right now, causality doesn't really feel like it plays into this, even though like when you talk about mechanism, it feels like hypothetically mechanism should be talking about the sort of causal interactions between the entities. Like
Well,
you could have a descriptive model that you could view as causal, and I think people commonly do this.
You're saying like the linear regression to predict a neural
Sure,
activity to
for
stimulus.
example.
We do assume that's causal
Yeah.
because we assume we're putting in the stimulus and that's leading to the neuron's activity, even though we acknowledge that the model doesn't map very well to anything.
But I think the distinction maybe is that it's not causal in a direct way. It's not causal. This gets at the mapping part. It's not causal in the way that maps to the entities in the real world. Like it's causal only at some coarse level of abstraction. I mean, again,
It's not picking out variables. Intervening variables is an old term from behaviorism. But yeah, that would be the idea, is that if it's not picking out intervening variables, then maybe it's not causal or something like that. The problem I have with all of these ways of characterizing the distinction is that once you shift down a level, all the things that were once intervening variables, now that's just behavior again.
Yeah.
And now you need more intervening variables. I mean, it all seems very contextual, and it's all properties of our explanatory practices. We're not really latching on to anything in terms of the objective mechanisms in the world. I think he might be okay with that. I think Kaplan is pretty well concerned with the epistemological aspects of explanation, and less so these ontological aspects. But he might be fine with all of that, with this idea that you need intervening variables in order to pick up on some of the mechanistic constituents in order to satisfy 3M. It's not enough to just say the neuron's firing rate was modulated by a change in the image. Rather, you need to be able to characterize the process by which the neuron's firing rate achieved what it was observed to be as a result of showing the image. That gives you a different knob to turn in order to manipulate that neuron. That might be something.
Like you want to be able to manipulate, as you said, intervening. So like properties of the transmission from the input to the neuron, like
that's
like
right.
other neurons.
Other
in the
neurons
chain.
in the middle, kind of, yeah.
And this also relates to a different point that he made that I think is really important about mechanistic models versus descriptive ones, which is this idea that a mechanistic model can generalize to different contexts. Like you could fit a descriptive model that really fits well, like what this neuron will do in response to these three images that are pretty similar to each other, and anything that's kind of very similar to those three images you can predict. But if you show it, even like the same image that has a different color, it won't be able to predict. So you could get a really good descriptive model in the sense that it's a really good fit to the data, but it can't be generalized at all, and that makes it unlikely to be a mechanistic model, because a mechanistic model would have all the different intervening parts, and so would be able to capture whatever else changes in the change of context, or when things that the model wasn't trained on are given to it.
Yeah, so I think that's an interesting point. Certainly it's the case that when you have a mechanistic model, you're going to have a representation of the system that, gives you more ideas about how you can go into the system to change it, and it also gives you a fuller account, Grace, like you were just saying, of the different behaviors that the model suggests the world will show in different conditions. But and this is a new objection that I've always had a problem with this kind of account, which is that mechanistic models are general in that sense. I agree, but they are limited in their application in a different sense, because, as he says, you want to fill in the details about the entities, the way the entities are interacting, And sometimes in science, what we actually want to do is leave out those details, because by putting together a model that skips some of the parts, the details of the parts, and the details of the activities, and the specifics of the way the parts interact, we get a more general model. So the difference of Gaussians example that he brings up, I think, is a good example of this. So briefly, he talks about how these retinal cells, the cells in the retina, they have a certain kind of stereotyped response where it's called center surround responses, where if you shine a light that is very focused in the center of where the cell fires a lot in the visual field, then you get this big, nice response. But if you shine a bigger light that sort of bleeds into the surround of the cell, you get a very depressed response. The cell reduces its firing rate. And that has been modeled as a difference, what's called a difference of Gaussians.
So, and also, just to be clear, in lay terms, what this usually connotes is that the cell responds most when there's a lot of contrast. So if it's very bright all the way around, the cell will not respond. If it's very dark, the cell will not respond. But if there's contrast, the cell will respond if there's a local contrast. And
that has been mathematically described using this difference of Gaussians. Now, the relevance of this to this generality point is the following. That model, the difference of Gaussians model, it's a nice way, actually, if you generalize to other types of cells and other parts of the system, it's a nice computational model that can describe kind of any sort of selective center surround kind of responses. So it's been hypothesized that action selection might work the same way, where the action you want in the basal ganglia, the neurons that represent that action are excited, and the neurons, the nearby actions in action space that are represented by other neurons are inhibited greatly. And so you kind of get this center surround type of organization for action selection.
So in abstract spaces, what this would mean would be let's say you wanted to say, I want to pick up this piece of food and bring it to my mouth. The other thing would be I want to scratch my ear using my hand, or I want to pick up a fork and put it somewhere else or something. Maybe these are similar things, and then I'm using my right hand to do something maybe vaguely near my face with all of these actions. And if you are to select the one that's pick up the piece of food and bring it to my mouth, it means that you're going to sort of suppress the possibility of activating all of these nearby actions of doing something with your right hand vaguely related to your face or something.
That's right. And it's also been used for working memory. It's been used actually for a number of other computations in the brain. And you kind of lose that aspect of the applicability of some of these models to different domains if you stick too closely to the mechanistic guns. So at one point in the article, Kaplan says something like, well, if you want to claim that these models are explanatory without being mechanistic, you need some grounds for their explanatory power. And he says, description isn't going to work. Prediction is what he calls predictivism. Prediction isn't going to work because there's too many models that are predictive that are not explanatory. And that's what we were talking about earlier with these merely descriptive models, or these P models, these phenomenological models. But he doesn't consider any other possible grounds for the explanatory power of these models. Now, earlier at the outset of our discussion, I gave a very brief history in the philosophy of scientific explanation, and I contrasted the classic covering law model with what's called the causal mechanical model, of which Kaplan is a good example. But of course, it was a very simplified presentation. There's a very robust, another thread in the tradition on unification, what's called unification as a grounds for explanatory power. And the idea here is something like the following. Scientific explanations, some anyways, proceed by describing phenomena and taking those descriptions and applying the models, applying the descriptions, however you want to think about it, to different domains that you wouldn't necessarily think are alike. So the most famous example of this has to do with Newton's physics, what are called Newtonian Kinematics. And the idea was that Newton took this set of mathematical models and he explained the behavior, the movement of terrestrial everyday objects, and he used those same models to explain the behavior of the heavens, celestial mechanics. So he unifies terrestrial and celestial mechanics. And that was considered an instance of unification that was explanatory, because what you're doing is you're saying, aha, I have found something like a regularity and it explains this behavior across these different domains. I've really latched onto some aspect of nature. And I think something similar can be said in defense of these mathematical models, namely that something like the difference of Gaussians, which can explain this retinal activity, but is also used to explain working memory and action selection, as we just described, maybe one of the ways that what he would otherwise call as a merely descriptive model, in fact, isn't merely descriptive because it gains explanatory power by unifying diverse phenomena.
Yeah, it's interesting.
I kind of like that, but I kind of feel like there are important differences between the physics example and the differences of Gaussian's stuff. Because part of, if you're really talking about specifically predicting things, part of why the difference of Gaussians approach can work, and when we say that, we literally mean like a subtraction of Gaussians. Like there's one curve and you subtract another one and you get a curve that captures this center surround response.
It's like a donut shape, basically.
Yeah, in 2 dimensions. And that has some parameters to it that make it more broad and can be applied to a lot of things. So I don't know if saying that model fits a lot of stuff is the same as saying like the actual exact same physical equations fit a lot of stuff. Because part of why it can fit a lot of stuff is that it has parameters that can be fit to fit it.
Yeah, right. I mean, I'm not so sure that's that different. I mean, if you think about like the universal law of gravitation, it applies to everything, literally. And it has parameters. It's got variables. You can change the values of the variables.
Well, no, but the point is like the gravitational constant's the same across all objects.
Yeah,
whereas
exactly.
in the difference of Gaussian, I'm not just to clarify the distinction between, right. So like in the difference of Gaussian's case, like it isn't like one universal law that applies everywhere. It's like a version of an approximately the same rule or heuristic is implemented possibly differently in different settings, and the same abstract principle.
Right, I see.
Is the
and
case.
there's not necessarily anything that's constant across those examples.
Yeah, it's not exactly constant. It's like the same computation is
exactly
performed, which people in neuroscience,
Right, but
there's this notion in neuroscience that a few people have advocated for of canonical computations, that it's like
Yes.
worth thinking about how the brain works in terms of it implements a few things like normalization and gain control or gain modulation and a few other computations.
Integrate to bound, linear filtering. There's a number of these. And you said normalization. Actually, there's one of the hot areas right now in philosophy of neuroscience is trying to figure out how to explain these canonical neural computations, these CNCs. And there's a couple papers, some pushing the mechanistic explanation right up Kaplan's alley, and others that have advocated for different reasons, different kinds of explanation. Right now in the philosophy of science, generally speaking, it's kind of the mechanist versus the non-mechanist, to put it.
So are you a non-mechanist? Is that what we're getting at?
I am sick of this debate, especially in the philosophy of neuroscience. I think there's so much more interesting stuff that goes on in neuroscience, and I think philosophers have a tendency to have hyper-focus on a few issues, and then there's this very rich epistemic and pragmatic and theoretical issues that get overlooked. I have a weird kind of mechanism. In my dissertation, I defended the idea that dynamical systems are kinds of mechanism, but they're not the typical kind of mechanism because the parts of dynamical systems aren't these spatial temporally characterized parts, and there's a number of other differences. I also wanted to point out something about the 3M constraint that the discussion reminded me of. So you can give other kind. The point, by the way, of bringing up Newton and the difference of Gaussians and how it can apply to all these different domains is that there's just other ways of thinking about explanatory power of computational models. But what's interesting about 3M is imagine I am Newton or whatever, and I've constructed the universal law of gravitation, and I'm looking at 3m. Does 3m match? Does my universal law of gravitation, is that an instance of 3m?
I think
Certainly,
no. Yeah.
there are variables in the model, and they seem to map onto things in the world, and these mathematical dependencies, like summing the masses and dividing by the radius squared, those seem to capture causal relations. It's the force of gravity.
I'm not even. There's still like weird, like gravity's weird. There's action at a distance, right? It's like you've got two big massive things separated by like a vacuum, and they're drawn to each other. That's the explanation. That's just the description. Like, if there's anything that's just a description, it is gravity.
Oh, you think that's just as... Regardless of what you think the explanatory chops are, it seems like to me that it might satisfy these constraints, and certainly it's the case that the mechanists want to try and differentiate themselves from the covering law people. And the point I'm just trying to make with this example is that it isn't obvious to me that your typical scientific law, or atypical, I don't really care, typically these laws, they mention stuff. They have variables that stand for things in the world. Those things in the world stand in certain relations and share certain properties and can be considered a mechanism, largely broadly construed. And these things stand in certain relations that could reflect causal dependencies. I understand the point about gravity, and maybe I would need to give a relativistic interpretation.
Yeah, you'd have to go to like a deeper physics-based, but I think even
Yeah,
that
let's
wouldn't
go
explain
deeper.
it either. Because even like, I mean, I don't want to get into a whole digression, but like, you could go pretty deep and it would still look a lot like a description, I think.
Right. But I guess I'm just trying to point out that, 3M might not have enough oomph to it to really play the theoretical and conceptual role that Kaplan wants to use it for, because he really doesn't say enough about what it takes for something to correspond to a component or an activity or an organizational feature, or on the other hand, he doesn't say enough about when one mathematical dependency that is posited among a group of variables in a model corresponds to a causal relation. I mean, he doesn't really give an analysis of that, but it's really doing a lot of work in the constraint.
Yeah, I think that's where my initial concern about it seeming to assume that you know the correct answer is showing up. Because, the idea that something becomes mechanistic when it captures the causal relationship feels like you have to know that that's what it's doing. And I don't actually see necessarily how this framework, this 3M framework, would resolve the issue that you brought up initially of if you have a sun and a flagpole and a shadow, how do you know what causes what? You could calculate the height of the flagpole via the shadow, but we know that's not the causal direction. So, except for the fact that he says it captures the causal relationship, I don't see how it resolves that issue, because that's not meant to be an explanation.
Good. So maybe earlier at the beginning you characterized that very cogent objection by saying it's circular. Maybe a more charitable way to put it would be he owes us an account of how we can determine causal correspondence, i.e. correspondence to a causal relation that isn't circular, that doesn't already assume we have that answer in hand. Would that be a fair way of recapitulating your objection?
Yes, I would like to hear more on that part of.
So, but I mean, okay, well, without getting into a whole other thing, I mean, like in science, we believe we can characterize causal roles of different variables by performing interventions, right? Like we believe we could change one thing and see what happens, and people call that causal. I think that's one definition of causality that like a lot of people will talk about, like if you think that this thing causes this thing, do an experiment to block it or knock it out or something like this and see if it has the effect on the thing you wanted. I think like people take that for granted, that is a way of characterizing causality through experiments, but I think in a lot of these examples that wouldn't work. So if we go back to even in the flagpole example, if you did an intervention and like grew the flagpole and it changed the size of the shadow, I guess the statement is you couldn't grow the shadow and change the size of the flagpole.
Yeah.
But you have to know that to know that you can even, like, if looking at it just as variables, it's like you've solved the problem if you know I can change the flagpole, but I can't change the shadow. And to me, that's the thing that like resolves this trick. But it also like for systems where you don't know which one causes which, or like it's not obvious how to action one versus the other. It's like not until you figure out how to independently perturb one of those things can you even test it. So it's like, but I do think that there's something to this, right? So like in the flagpole case, like you would have to know what the underlying model is to know that you could do one of the interventions, basically.
Yeah. Yeah. That is the advantage of the manipulationist interpretation, that it does get around some of these issues by enforcing further constraints. But those constraints, which that would be a whole nother discussion, but I just want to point out those constraints are not in 3M.
Yeah.
Yeah.
But maybe that's one way to get around this issue.
So I think we can start wrapping up. I feel like my takeaways are that there should be more gradation to this. It shouldn't be a dichotomy between descriptive and explanatory. It should be a continuum. And also I think another thing that came up a lot was like recursion. What looks like implementation details on one level is not, if you go down. And so this is all kind of relative to some hierarchy that we assume exists. And there was one other thing that he brought up in the conclusion that I want to touch on that seemed not necessarily related to much of this, but I thought it was interesting. He seemed to chastise either mechanists or neuroscientists who are also mechanists, I'm not sure who it was thrown at, for not forcefully arguing for the role of math as mechanistic models, for mathematical equations as mechanistic models, and says that there's an over-reliance on visual models like diagrams and box and arrow models and that kind of thing. And that came a little bit out of nowhere to me. But I mean, I agree somewhat. I think people should be more explicit. But it did seem like a lot of what he was talking about isn't specific to math. Like you could apply the same analysis to a box and arrow diagram. But yeah, he said the anemic effort on the part of mechanists to address the role of mathematical modeling in mechanistic explanation, he was angry about.
Yeah, that's a call out to the philosophy people.
Okay.
And for the need to give an account that reflects the important and central role that mathematics plays in characterizing mechanisms.
Do you think all of this could be done, this analysis could be done on visual models, like diagrams?
That is an interesting question. I mean, I'm kind of a pluralist about all these things. So for me, it's like, do a little bit of math, do a little bit of models, build a representation, both on paper, in your computer, in your head. I'm a pluralist about explanation. Some explanations are mechanistic, some are law-based, some are what are called structural explanations. I didn't get a chance to really go down the litany of all these different types of explanations because there's 1,000,001 non-mechanistic approaches. But one idea is that you can explain something just by picking out general topological features of a system, sort of how the system is organized. Sometimes systems have to act a certain way because the domain within which they're acting is structured a certain way. You just can't. You can actually get insight into why a system is behaving because it's doing a certain thing, and there's really nothing else it can do if it's doing that thing. So I'm a little bit of everything. I'm kind of like, when it comes to explanation, I'm a real pluralist. So yeah, could you do it completely using visual diagrams? I don't know. That's an interesting question. And maybe it depends on your audience. I think some scientists, if you give them a diagram, sometimes that's all they need to...
I feel like it has to do with levels of precision. So this is related to your statement if it has to do with the audience. I mean, I feel like there's a sense in which once you've learned how to state things in math, it's like, why would you not state it in math? Because you could be much more precise. But I think you can't make every statement so precise. So if you have, I think... that was a bit of, hopefully it was clear that was a bit of a joke, right? Like there are statements that are like inherently fuzzier statements that you want to make, and you wouldn't use math to describe them because you don't yet know how to state them with a certain degree of precision, but they're still worth stating.
And then there's cases where I can show you a very simple diagram and I don't need to mathematize it because I know in virtue of the content of the diagram, you of your own accord will bring to mind the appropriate mathematical formula.
If you're literate in it.
And so, yeah, if you're very familiar with it. So, I don't know. You got to know your audience, right? It's like any kind of discussion. But could you communicate it to a lay audience or to a non-specialist in the field? I think you would need math. I think you would need that kind of precision that is so central to the sciences. And so I think in that context, I endorse Josh's position. If you can describe it with that level of precision, you just do.
Does anyone have any other closing thoughts or summaries?
I like ending it on the math statement. So
I will say, I mean, there's a lot of really great work now in philosophy and neuroscience. It's really an exploding field. Carl Craver, who's one of these new mechanists, he's one of the three in the Machmer, Darden, Craver new mechanism explosion from 2000. He has a 2007 book called Explaining the Brain, which is very good. And I'd like to, I should plug that. That's a really great book and a good place to start for anyone who's interested in more philosophy and neuroscience. And then, it's good stuff.
And if you can imagine, even after this conversation, there is stuff in this paper that we didn't even talk about. So people can read this paper if they want to know more of the details. There's another example of models in computational neuroscience and other ideas that we didn't really talk about. So that will be on our website, as the papers we read always are. Well, thank you, David, for teaching us about philosophy. And
thank you guys so much for having me on. This was really good fun. I'd love to do it again sometime.
Okay, great. We will remember that. Till next time. Hey, if you're still listening to this, you must really like us. So how about you go to iTunes or Stitcher and rate the podcast, give us some feedback. You can also go to our website, unsupervisedthinkingpodcast.blogspot.com. You can comment on different episodes, or you could give us ideas for new topics you want to hear about. We would love to hear from you. Thanks.